It is time to arm ourselves with another tool that we can use in our networks, and that is the spanning tree protocol. We're going to take a look at what spanning tree protocol is all about and how it helps in a good switch design. We'll start off by taking a look at some good switch design practices. I mean, we've moved from the ccENT level now into the CCNA. So our networks have grown from the small business network to a medium to enterprise class local area network environment where our switches tend to be like rabbits. You leave them in a room for a while and you come back and there's just switches everywhere and you go, how do I manage this? We'll take a look at some good switching design practices to handle the multiplying switches. We'll then look at what switch loops are, because that's one of the crises that you run into when you're setting up a large switch network. And then we'll see how to stop the switch loops. I'll give you the answer right now. It's spanning tree protocol. So after we talk about what spanning tree does, we'll get into the specifics of spanning tree operation. Spanning tree is one of those protocols that has a very simple goal, but there's a lot of complexity in how it accomplishes that goal. When you design a switch network, it's best to approach it in layers and to take a layered approach. What you see right here is a picture of an extremely large network that is designed in 3 separate layers that Cisco has dictated as the access layer, distribution layer, and the core layer. And it's kind of hard for me to talk about this picture without really getting into the growth of a network. Imagine yourself. Imagine you created a company that makes iPhone accessories. The Apple iPhone, they make accessories for that. Now, when you create this company, you start off with you and 10 employees. Are you going to deploy a switch network that looks like this? No. Not for 10 people unless you're just going for way overkill. You are going to deploy a network that looks something like, oh, where's my pen? Something like this, where we have one switch with our 10 employees attached and maybe some little, not even a Cisco. You've got like a little Netgear or something connecting you off to the internet. Now your iPhone accessory store starts to grow and you hire a few more people to produce those accessories. And so you don't move to a model again like this. You just plug in another switch with a crossover cable and attach those users right there. And you continue to grow and eventually max out those 2 switches and plug in another switch in there, and now you've got your official servers on your network. You're still probably using a Netgear. You've got 50, 60 different employees that are working out of the office, and you're starting to get a little nervous feeling in your system because you've been daisy chaining these switches. They're almost all maxed out, but you also know if any one of those switches go down, you're going to cut your network in half and you're going to have a pretty catastrophic outage, which when your company has grown to this point, people are depending on those systems to be in place. So what you do is you take all the money you've been making out of your store, you take all those switches, put them in a closet somewhere, and you buy one of these switches, which is maybe a Cisco 4000 series or 6500 series switch that has a bunch of blades. You got the dual fan tray action, you got the dual redundant power supply down here. This is where the plugs go in, and you got the fans and the power supply that kicks on, makes a lot of noise. You got the big mother of all switch, and all these devices are plugging in there. You now have upgraded to a Cisco router that connects you off to the internet, and eventually you just keep on going and max out this switch, and you start daisy chaining your old switches that you pull out of the closet from this guy to get some more ports, and at this point you're probably in the hundreds of employees at the company. And you start to get that nervous feeling in your system again, thinking, well, this is a great switch. It's got the dual power supplies and fan trays and supervisor modules and all that kind of stuff. But what if that switch goes down? That's the core of my whole company. So that's where you buy a second one. You got money at this point, right? So you get a second one, hook them up to where they're redundant and they back each other up. And now you're starting to approach a model that looks like this, where you have distribution layer switches, which are providing core services, or essentially routing services, VLAN services, and so on, that are attached down here to access layer switches. Now, with this layered approach, it allows you to have easy and manageable growth. And this is Cisco's model. They created this model right here. The access layer is where the devices actually plug into the network. We have servers connecting to the network on their access layer switch, PCs plugging into the network on their switches. The distribution layer is where your major segments happen. You have kind of these modules that are created here. You know, maybe you've got your sales group over here, which has 100 or 200, 300 different salespeople inside of it. Or it could be floor 4 of your building that you own. You know, you've segmented into one big group. You've got the dual redundant 4500 or 6500 series switches there. Over here, you've got your server farm network where all your servers are isolated. You have a separate VLAN over here for that. And now you eventually reach a core layer. And when you get to this point, you're probably at thousands of employees. The core layer is considered the backbone of a network. Now think of this as a campus model. And when I say campus, I'm talking about a literal college campus. Or maybe you have the College of Business over here. You've got the College of Art over here. And you know, all the different colleges, and they all tie back to the backbone of the entire campus network, which is the core, and everything goes through the core, and you have other buildings that branch off of here with modules that look like this. So that's the idea of designing a network in a layered approach, is designing it with modules. And you see down here a new term, ether channel, can provide for more bandwidth on key links. What ether channel is where you can do something like this. You see these 3 lines going between these? Maybe you've got so much traffic passing through the backbone that just one 100 megabit per second or 1000 megabit per second port isn't enough. What ether channel can do is it can actually take between 2 and 8 ports. You can go up to 8 and bundle them together into a single pipe. So you could have your 2 switches right here. And if these were 2 100 megabit per second ports, ether channel allows you to tie them together and get 200 megabits per second of throughput. So that way you can have, you know, add a bunch of links in there and channel them all to get super high bandwidth links between your switches. Now, the last point I want to make, and the reason we're talking about this ideal design right here in this video section, is the redundant connection. The redundant connections eliminate a single point of failure. So when I have my access layer switch, notice I always have a crossover cable going to both distribution layer switches. The distribution layer switches always has a cable going to both core layer switches, so that if any one device fails in the network, we have a backup path that can get us around that failure. So redundancy is good. We've determined that. But unless you design it the right way, redundancy can be very bad. To understand why that redundancy is very bad or can be bad, you have to understand how the switches are going to treat those redundant links. By default, a switch will send broadcast packets out all ports. That's how they're designed. So when this computer sends a broadcast packet into the network, the switch says, oh, I don't know where that goes. I'll send it out every single port except the one I received it on. So out those 2 ports it goes. This switch receives it and sends it out to this computer because that's a port. And then as it receives it on this port, it loops it right back to that one. And as it receives it on this port, it loops it right back to that one. Again, the switch receives it on both those ports and sends it back out to this PC and then loops right back around. This will keep happening eternally, meaning this broadcast will cycle the network, blowing up all the devices on the network until you shut down the whole network, meaning turning everything off. A lot of you might be thinking, well, wait a sec, I've heard inside of a packet is this field called the TTL. That's the time to live, how long a packet survives. But the TTL is a layer 3 field, meaning it's up at the network layer. Only a router can subtract time from the time to live. Now looking at that picture right there, do you see any routers? Nope. So what's going to happen is that packet's going to cycle the network round and round and round and round, destroying everything that's out there. So while the redundant connections are necessary in business networks, we have to have a system to manage them so they're not all active at the same time. Because if they were, we'd have that broadcast problem. So the place of spanning tree is to drop trees on redundant links. That's my little way of remembering it, because there's so often you get all these terms and then spanning tree comes out there and you're like, what did that do? Just think of a falling tree. It's falling on all the redundant links in the network. What spanning tree does is find all the best links in your organization. For example, It looked at that link, and for some reason or another, we'll talk about those reasons in a moment, it said that link is better than that link. So I want that one to be active. So the tree falls on this redundant link and it goes inactive to where it's not in use. So this one's forwarding along, life is good, until, maybe the cable goes bad or the port gets shut down or something like that. Spanning tree is always watching the network, and if something occurs, it's going to take that tree and lift it right back up. It's going to say, okay, life is good. Let's go ahead and unblock our redundant connection and allow traffic to forward here until we see our main link, which is better for some reason. Our main link come back online, then we can go ahead and drop the tree on our redundant link again to make it inactive. Spanning tree is one of those concepts that is sometimes difficult for me to talk about because what I described to you right then is all it does. That's the whole goal of spanning tree. But go to Google and type in spanning tree protocol and just see how many pages and pages and books of information are out there on spanning tree. You might think, well, if that's all it does is block the redundant links, what's the point of writing a book about it? Well, networks are not as simple as what I just showed you, where we have two individual switches connected together. Networks have hundreds of switches, and the spanning tree has to find what's the best ones to block, because if it blocks the wrong one, you're going to have a very inefficient network. So here's the facts. The original spanning tree protocol, its official standard, is 802.1d. That's the technical name for it, was created to prevent loops. The switches will send probes into the network called BPDUs, or Bridge Protocol Data Units, to discover loops. So what's going to happen, again, take our little topology there of our two switches. If we have two switches that run spanning tree, they will send probes on the network. Now those probes are kind of like broadcast packets. They're actually technically multicast. And they'll come into the switch, and all this probe is, this BPDU, is a little identifier for the switch. So say this is switch 1 and this is switch 2. Switch 1 sends a probe into the network and says, pew, let's say, think of like sonar sounds, boom, and sends out a little probe. Now that message comes into the switch, and since it's a multicast, or it's designed kind of like a broadcast packet, it will loop it back around. Switch 1 will get the probe, open it back up, and look inside and go, whoa, this is my probe. I sent this out, meaning I see my name inside of this probe. That means there's some kind of loop in the network. So that's when they go into action. These probes also help elect the core switch of the network, known as the root bridge. There's our key term. In our switch network, say we've got bunches and bunches of switches all around the network that are all tied together with redundant connections going everywhere. In that case, we will have one switch which will be elected the root. Now that is considered the core switch of the network because all the switches will find the best way to reach that root bridge, then block all the redundant links. Meaning this one's going to look and say, well, the easiest and fastest way for me to get there is this link, so it's good. But I've noticed that I can also reach the root through this link and, well, not that link down there. So I'll block that redundant connection. Okay, so all the switches find the best way to reach the root and then block redundancy. So the key of spanning tree protocol is to make sure you're very accurate in the one that you elect as the root bridge. The thing that could work out horrible for your network is if you just let spanning tree treat everything at default. Now I'm jumping a little ahead of myself, but by default, spanning tree will elect the oldest switch in your network as the root bridge. Now, I don't mean oldest as in how long it's been running. I mean oldest as in manufacturing date. So some little, 10 megabit per second 1992 switch that you have stuck in a wiring closet that you forgot about gets elected as the root, and everybody's like, hey, that's the root. Let's find the best way to get there because that must be the center of the network. Everybody finds the best way to the closet switch, and your network performs horribly. And the problem is nobody really knows why. Nobody can really put a finger on it because it looks like everything's designed right. I mean, you're using great equipment and servers are working. It's just things just run slow. And yet people just find, I guess that's the way it is. And you run this beautifully expensive network that you've invested all this money into that never performs quite like it should. Now, I should also mention that every Cisco switch runs spanning tree by default. So you can plug a network together with redundant connections, and it's not going to have any loops. It's just that it's going to be a very inefficient network. Now, I should also keep in mind that you are at a CCNA topic at this point. It's not this topic isn't in the CCENT material or the icnd2 video series you might have already seen, because this is something that works for enterprise networks. Meaning, in a CCENT level network, you're not going to have hundreds of switches. You won't even have 10 to 20 switches because CCNT is focused around small businesses. So when you get to the larger networks, the mid-size, the enterprise networks, that's where Spanning Tree really plays a role, and a big role at that. It has to elect the best switch as the root bridge. So when we're understanding our Spanning Tree network, we need to understand more about these BPDUs and how the elections work. The way that the elections will happen is all the different devices in the network have something known as a bridge ID. That's their name to Spanning Tree. Remember I said we had like switch 1, switch 2? Well, it's not that the switches don't really care about their host name. They care about their bridge ID. Now that bridge ID is built of two pieces. You have a priority and you have the switch's MAC address. I'll just put MAC add. Okay. You can see I put priority dot MAC address. Now by default, every switch, when you pull it out of the box, has the same priority, 32,768. You know, somebody just took a dart and threw it at the dartboard, and they're like, yeah, let's make it 32,768. Now, I should mention the priority is kind of counterintuitive. When you think of priority, you think, oh, bigger priority, that's better, right? Not so. Lower is better. So the lower your priority, the more chance you have to be elected as the root bridge. Now, since all the priorities are tied when you pull these switches out of the box, it has to resort to the MAC address to break the tie. Now we're getting to the reason why the oldest switch in the network becomes the root bridge. When the manufacturers manufacture switches, they will start with the MAC address that's lowest in their range. Meaning, you know, say you're Cisco. You'll go to the powers that be and acquire a MAC address range that you can use for all your devices. You'll start manufacturing devices and start from the lowest MAC address and just keep increasing the MAC addresses of your devices as it goes. Now keep in mind, I'm talking about the MAC address of the switch, not one of the MAC addresses that it's learned about that's from a device that's plugged in. The switch itself has a MAC address. So when we have this kind of scenario, obviously I just made up these MAC addresses, AAA, BBB, CCC. This one will end up being the root bridge because it has the lowest MAC address of the three. So once that root election happens, all the switches in the network settle and they say, okay, that one is the root bridge. Now let's find the best way to get to that root bridge. Now you notice right in the middle of the picture right here, I have a link cost equals 19. There's a table. I'm going to bring up that table in just a few that shows all the different speeds of links that you have, like 1,000 megs per second, 100 megs per second, 10 megs per second, you know, and down and down and out it goes. Now, if you have a 10 meg per second link, the cost to Spanning Tree is actually 100. 100 megabit per second link is 19. And I'll show you the chart later on. But that's how it determines the best way around the network is based on the link cost. So it says, okay, if this is 100 meg link, it's 19, 19, 19. We'll just say it's all 100 meg link everywhere. All the switches in the network try and find the best way to get to the root. This one looks and it says, well, I see a cost of 19 to get that way, a cost of 19 plus 19 that way. So my root port, I'll just put RP on there, is going to be right here because that is the most efficient way to reach the root bridge. This one does the same and elects this one as its root port. That's the best way to get there. Now the root bridge, you know, it's the king of the network, and as its reward, it will never block one of its ports. And by the way, a root bridge will never have a root port because those are used to reach the root bridge. Obviously, if it is the root bridge, it doesn't need to reach itself. So down below, you can see the next type of port is a designated port. The designated port is just a forwarding port. I wish they would have chose that name instead of saying designated port. Designated port means there's one port that is forwarding. Now there is one designated port per link. Now this gets kind of confusing. A link is a segment between switches, or I guess you could say a link is just a switch port, or a link between the switches. If I have a PC attached to this switch, this would be a designated port, meaning a port that is forwarding because it works. You know, another PC over here, that's a designated port. It's plugged into a port that is forwarding. Now, when it comes to a link between switches, you will have one forwarding port per link. Now, you're kind of looking at this picture, and I guess I should back up a step. Is that picture a demonstration of a redundant topology? Yeah, sure it is. Because if this is switch, we'll just say this is switch 1, switch 2, and switch 3. If switch 1 goes down and dies, well, switch 3 can still reach switch 2 and still has active connections. If switch 2 were to die, switch 1 could still reach switch 3. It's redundant. But remember, a broadcast, if we don't block something, will circle around and around that network everywhere, blowing up all the devices. So when you are talking about these links, we know one of them has to go, and we know now that these are using these paths to reach the root, we know that it's going to be this guy. We know that link is going to die. But before it dies, we have to realize that every link has to have one designated port, meaning one of these must stay forwarding. In this case, it will be this one, DP, designated port. The other side will assume a blocking state, meaning ka-chunk, ka-chunk, switch 3 blocks its port. Now it's kind of obnoxious because if you're sitting on switch 1 doing show commands, it's going to be like, oh yeah, that port is great. It's forwarding. Life is good. And you're going to think to yourself, wow, I thought I understood spanning tree. Why is that forwarding? I thought that link would go down. Well, it is down because if you block one side of the link, the other side can't communicate, so it's disabled, but you have to be on switch 3 to be able to figure that out. Now, I want to answer a question that I think is probably circling around some of your minds. You might be thinking, well, why is that side the designated port and this side get blocked? Why didn't this side get blocked and that one be designated? Well, take a guess. Look, knowing what you know about spanning tree, why do you think that would be so? Remember these. Bridge IDs. The bridge ID is that combination of priority and MAC address. It's not only used to elect the root bridge, whoever has the lowest one in the whole network becomes the root, but it's also used to determine who's going to block the link. Again, lower is better, so since this guy is lower, he's like, I'm not blocking my link. Switch 3, you're lower than me, or higher. So your priority is lower, or wait a sec, I'm going to stop talking. Switch 3 is not as good as switch 2. So it's going to block its link and disable that, effectively taking the whole thing down. Now, if any one of these links ever dies, spanning tree will recognize that, and it will unblock this link to resume the connectivity, even though one of the switches failed in your network. I want to point out that even in a network this small, the switch that becomes the root affects what links get used. So let me just clear off all this chicken scratch. We said this one, and let me get to where I can draw again. We said this one is going to be the root, so these links stay active, and these switches go through this switch to reach each other because this one gets blocked. But if let's say this one over here gets elected to the root, then which link gets blocked? This one. Because these switches will say, these are my root ports, that's the best way to get to the root bridge, and they will go through this switch to reach each other. And now I think you can start to see why it's so critical that you play a role in who becomes the root bridge. Because if this is the oldest switch in your network, and these two switches have to go through that switch to reach each other, then this guy is going to become a bottleneck because it's not going to have the speed and capacity that some of the newer, bigger switches in the network are going to have. And I think you can already begin pondering how you're able to influence the root election. You know how a root bridge is selected. It's the priority plus the MAC address. Well, you can't change the MAC address. That's set on the switch. It's hard-coded. But you can change the priority. So by dropping that number down and lowering that, you can influence the election. At this point, I think we're getting the feel for spanning tree and what it does and how it does what it does. So here are the official 2 major steps to how spanning tree finds the best path. Step 1. Elect the root. If we had our little three switch networks, and by the way, anytime you're learning spanning tree, that's the normal topology that you have. Once you elect the root, then the switches will find the lowest cost path to the root. So they're going to look at the link speeds that they have and say, well, the lowest cost path, if these are all 100 megabits per second, they're all a cost of 19, 19, 19, and they'll all find the best way to the root. Now, just to give you an idea, if we had a low speed link, let's say this one was a 10 meg link, then it'll be a cost of 100. So this switch will say, well, it's either 100 to go that way or 38 to go that way. So that's the more efficient way. I'm going to block that link. So the cost or the speed of the links really do have an influence. Now, I want to add in a couple pieces here because I know some of you might be thinking of the bigger, more advanced topologies. What if you had a situation like this? What if that was the root and this switch was trying to figure out what link to block? Now remember, this is redundant. We have to block one of these links, but if all of these were equals, let's say they were all 1 gigabit per second connection, well then both paths are a cost of 8 for that switch down here to reach the root. What it's going to do to break the tie is it's going to choose the switch, the upstream switch, with the lower bridge ID. Meaning, again, remember that priority we had, 32.768 dot, and then the MAC address. If this MAC address is lower than this one over here, then it's going to say you're the best route. If the other side was lower, it would say you're the best route and block the opposite one. There's only one more topology that can throw a fork in the wrench, and that was the original one I showed you when I was saying what spanning tree did. What if you got a situation like that? Both of these we'll say are a gigabit per second, so they're both a cost of 4. That guy's the root. This one, you remember, the root never blocks a port, so this switch has to figure out which port to block to stop this redundancy. The costs are tied. The upstream switch is the same, so it can't use the method we used over here to break the tie. So what it's going to do is prefer the lower port. Just remember in spanning tree, lower is better on everything. It's going to say, I have to block one, so since you are the higher port, I will block you. And this one becomes the active link. This one gets the tree dropped on it. That is the basic concepts of spanning tree. If you want to have a good, well-designed, redundant network, then spanning tree has to play a role because you have to have something to disable those redundant connections until you need them. So we talked about what some good switching practices were, some design pictures of how we should design our network in the 3 layers, access, distribution, and core, with redundant connections across all of them. We saw what switch loops are and how to stop them. The switch loops happen anytime you have redundancy inside of a switched or layer 2 environment, and we stop them by using the spanning tree protocol. Finally, we looked at some of the specifics of spanning tree operation, like the root bridge election, like the bridge priority and the bridge MAC address, combining to create the bridge ID that's used to elect the root, and then how all the switches find the best way to reach that root bridge. Those concepts are critical for when we get into the next video, which is going to be configuring a little bit of spanning tree, and then we'll get into some of the enhancements that make spanning tree better and faster for our networks of today. I hope this has been informative for you, and I'd like to thank you for viewing.